Hey, welcome back to Fan Mama Physics. In this video, we are going to talk about escape velocity. So applying the escape velocity equation, which, if you don't have already, this is V escape is equal to the square root of 2 big G, big M of whoever mass this gravitational field we're trying to escape from, divided by r, which is the distance you are away from this object that you're trying to escape from. So let's start off with, you know what? I'm going to quickly do example 1, then I'm going to focus this video mostly on example 2, which is the Schwarzschild radius related to black holes and how we're unable to escape them. Okay, so example 1. At what speed do you need to throw the 1 kilogram rock in order for it to leave the Earth's gravitational pull, assuming this is on Earth? So a few things we need to know for that to happen is we need to know the mass of the Earth and we need to know the radius of the Earth, which is not provided in this question, but it is not assumed that you know that. It should be provided. So mass of the Earth is 5.97-ish to the times 10 to the power of 24 kilograms, and the radius of the Earth is approximately 6.38 times 10 to the power of 6 meters. So let's just do a quick calculation of this one. So 2 times 6.67, so Newton's universal gravitational constant, times the mass of the Earth, and all of that divided by the radius of the Earth, assuming that is how far the rock is away from the center of the Earth. Then you take the entire square root. So notice one thing about this is that the mass of the rock actually doesn't matter. You just need essentially that much escape velocity for your whole thing to leave. So whatever mass you need, whatever mass it's trying to escape, that's the velocity needed. Meaning if you have more mass, of course, you're going to need more energy to get this object out of the gravitational influence, but the speed is all the same. So here we got 11172, which is meters per second, then that's going to round to 2 sig fig, so 11,000 meters per second, okay? So, no, the mass of the rock did not, the rock of the rock. Does the rock of the rock matter? Yeah, no. Does the mass of the rock matter? No, it does not matter. How much kinetic energy would it need? Yes, then of course, you would need to use the speed and 1/2 mv squared to find the kinetic energy. So yes, the heavier the object, the mass of the object, the more kinetic energy needed for it to escape to infinity, okay? Okay, so on to example 2, which is what I want to really talk about in this question. Maybe I'll move my mic a little closer. I can't speak very loud here. Okay, so, oh yay, louder. Use the escape velocity equation, rearrange it to obtain the Schwarzschild radius, where c is the speed of light and rs is the Schwarzschild radius. So what is the Schwarzschild radius? It's a radius needed for start so that nothing, not even light, can escape from it. And usually we use it for the measuring the radius of a black hole. So really what the general idea of this one is that for Schwarzschild radius, if I take anything like this calculator in front of me, if I take this calculator and I but I compress it to essentially very, very, very high density, of which the mass of compresses to like a little tiny sphere that you probably can't even see. The distance from the center of this calculator, which is probably you can't see, to the outside, that's the radius which we're talking about. So that rate, if assuming that this mass, this calculator is that tiny, the Schwarzschild rate, if an object at that Schwarzschild radius, let's say it's right there, let's say that's my calculator compressed into this little highly dense ball, the Schwarzschild radius from there to there, if I place let's say I place a mosquito there, which I don't even know if that's going to be possible, essentially this mosquito would have to have a speed larger than the speed of light to be able to leave the gravitational influence of my graphing calculator. And imagine how dense that would have to be in order for the calculator to basically I need this calculator to give me the density of a black hole, which imagine how much energy that is going to require. But if you have something really massive like a black hole, then the mass itself is going to be able to provide that gravitational attraction on its mass so that it condenses itself to a really tiny ball of mass. So if this was a black hole, this was a Schwarzschild radius, which we use to find basically the actual radius of the black hole, then any person on at the Schwarzschild radius needs to have a speed higher than the speed of light to escape. So we often so this is the application. But we could hypothetically do this for any sort of mass, but of course it's not going to be realistic because you would have to compress that mass to a very high density in which you need some sort of other form of energy other than gravitational potential energy, which doesn't exist since the mass is too low for that. Okay, so, but let's get going. We know from the escape velocity, v escape, is going to be equal to 2 big G over m, and then this is going to be r, which is going to be our Schwarzschild radius from the center of this object. Okay, so that taking the square root. We also know that this escape velocity will have to be light because we're assuming that we need a speed greater than light in order for us to escape. So that's going to be c, which I will use for speed of light. Rearranging this equation, first of all, we're going to have to square both sides. And then we're going to rearrange for the Schwarzschild radius. So I would have to multiply this guy up to the other side in order to make it on top. And of course, last but not least, divide both sides by the speed of light to isolate for rs, which this is going to give me rs is equal to 2 big G big M over c squared. Okay, so that is the Schwarzschild radius. So let's see how we can use this one. So this is also in your textbook. If you have a SOCOS textbook, we want to compute the Schwarzschild radius of Earth and of the Sun. We will use this mass for the Sun and this mass for the Earth. So basically, we are saying that if we had to compress the Earth to a very tiny ball of mass, how big would it be, or what would be the radius from the center to the surface? And the same thing for the Sun. So let's do a quick calculation here. Let's do it for the Earth. Well, let's do this for the Sun first, since it was given first. Okay, so this is 2 times 6.67 times 10 to the power negative 11. The mass of the Earth will take as, the Sun, 2 times 10 to the power of 30 kilograms, which is quite massive, divided by the speed of light, which is 3 times 10 to the power 8, and that is squared. That's going to give us 2964. So that's going to round to, in this question, 3.0 times 10 to the power of 3 meters. That's essentially 3 kilometers. So 3 kilometers from the center outwards, a total diameter of 6 kilometers. So imagine the Sun has a diameter of 6 kilometers. That's how you would get the Sun to act like a black hole, which not gonna happen. So that's how much. Imagine you have to compress the Sun to that size. That's going to be very difficult. Next up, we have mass of the Earth. So let's do the same calculation for mass of the Earth, in which the Earth's mass is going to be, said in the question, 6 times 10 to the power 24 kilos. Putting in this in our calculator, I get 0.00889, and this is going to round up to, let's say 1/6 fig, so 0.009 meters, or in other words, 9 millimeters. So basically, imagine the radius of the Earth was the size of my nail, like how big my fingernail is. and double that is going to be my like a digit on my finger. Imagine the Earth's mass was condensed into this much space. That's how the Earth would act like a black hole, so that anything on the surface of this is Earth black hole would have to have the speed of light, greater than the speed of light, in order for it to escape. So that's the idea of a Schwarzschild radius, but most of the time we use this to find the radius of a black hole. Not necessarily. It's just hypothetical for the other masses. Okay, well, there you go. There's some applications of escape velocity. So keep in mind, this escape velocity we use only for objects that are at rest. We haven't said anything about escape velocity if something is in orbit. That's probably going to use a different equation, because this assumes the derivation of this escape velocity was assuming that the object is at rest and will need to gain enough kinetic energy from rest in order for it to escape. Okay, so that's it for this question. Thank you for watching this video. Good luck with your practices. Fat Mama Physics signing out.